Hello, my name is Kaundinya Vacha, and I would like to tell you about CertRL, formalizing convergence proofs of value and policy iteration in Coq. This work was done while I was an intern at IBM Research with my team consisting of Avi Shinar, Barry Traeger, Vasily Pestun, and Nathan Fulton. Reinforcement learning algorithms solve decision-making problems in which the goal is to choose actions that maximize a quantitative utility function. There have been a lot of high-profile applications of reinforcement learning, which include beating the world's best players at Go, competing against top professionals in Dota, improving protein structure prediction, and other successes which are too long to list here. Because of these successes, recent applications of machine reinforcement learning includes settings where safety and correctness are critical. And it is to this end that we got the idea of creating formalized convergence proofs of reinforcement learning. This is a typical reinforcement learning loop. It consists of an agent along with an environment. The agent is in a state in which it performs certain actions, and the environment responds to those actions by rewarding the agent with a reward and transferring the agent to a new state, and the cycle continues. This loop then generates a trajectory of states, which and also rewards. If you start, the agent starts off at a state S0, performs action A0, moves to state S1, at which point it retrieves a reward R1, and then it performs action A1 and moves to state 2 and receives action R2, and so on. A policy is a map from states to actions. And to each such policy, the long-term value of a policy is defined as the discounted sum of the rewards which are generated by the policy pi. This discount factor gives more weight to the recent reward and less weights to the rewards which occur in the future. The goal of a reinforcement learning algorithm is to find a policy mapping from states to actions that maximizes the agent's long-term reward. This is an example which illustrates some of the abstract theory which I've been talking about so far. Here, the agent is a turtle, and the states are these grades of a matrix. Some states are good for the turtle, some states are bad. For example, the red squares are bad and will give the turtle a low reward, and the green square gives the highest reward, and the stars give moderate amounts of rewards. The actions available to the turtle are moving up, down, left, right at each state. And the goal of a reinforcement learning algorithm is to find an optimal series of actions so that at each state, the long-term value which the turtle gets is maximized. So as I said before, reinforcement learning algorithms produce at a minimum a policy that specifies which action should be taken in a given state. The primary correctness property, which reinforcement learning algorithms is convergence, which means that in the limit, a reinforcement learning algorithm should converge to a policy that optimizes for long-term value. Our library, CertRL, contains a Coq formalization of two canonical reinforcement learning algorithms called value iteration and policy iteration. These are canonical because they are often taught as the first reinforcement learning algorithms in machine learning courses. Their convergence proofs contain the main ingredients for a typical convergence argument for a reinforcement learning algorithm. And in most implementations, their convergence is usually assumed implicit. Our formalization is available at the following GitHub link. It is part of a bigger project to formalize machine learning theory with possible applications to program synthesis. I should also say that all of the all instances where we have a flower in the slides and also in the paper point to formal equivalents in a hosted web page. So if you are following the paper, you can click on the flowers so to take you to the appropriate cork formalization in the project. Okay. Any specification of value and policy iteration must begin with a definition of Markov decision processes. A Markov decision process is simply a record or an inductive type with one constructor consisting of the following fields. There is a state space, which is a type, and an action space is a dependent type on the states. So for each state, you have an associated type of actions available. We enforce hypotheses that the state space and the fibered action spaces are all finite, and they're also non-empty. Also, the most important two fields are the probabilistic transition structure and the reward. The reward simply assigns a real number as soon as you move from state S to S prime by taking action A. And the probabilistic transition structure assigns a probability distribution for every state and for every action available at that state. The PMF, which you see in the type of the transition structure T, is the type of all discrete probability distributions over states. Now, I mentioned before that a typical reinforcement loop, learning loop continues. Sometimes the set of the loop may be infinite or finite. If it is infinite, the Markov decision process is called infinite horizon, and if it is finite, it's called finite horizon. For the rest of the talk, until the very end, I will consider infinite horizon gamma discounted Markov decision processes with appropriate reward functions, appropriate long-term value functions, which I will state in a moment. Now, a decision rule is a mapping from states to actions at one instant in time. And so in the finite time horizon case, because there's only a finite time horizon, at each time step, a particular decision rule is taken, and such a list of decision rules is called a policy. The analogous definition in the infinite time horizon case is a stream of decision rules. Now, the most important class of policies are stationary policies in which the agent performs the same action prescribed by the same policy. That means you perform the same decision rule at every instant in time. And such a policy is called a stationary policy because you do not change what decision rule you take. From now on, we also consider stationary policies, except at the very end where we drop this hypothesis in the finite time horizon case. The transition of a Markov decision process are stochastic. This means that if the agent at state S performs an action A, the next state can only be prescribed up to a particular probability. For example, going back to the turtle example for a moment, there's only a certain probability that the turtle will perform the action at each state. And this is what is enforced by the stochastic nature of the problem. However, in such stochastic environments, we are usually interested in the behavior of the agent and steps from the present. And so typical questions to ask are things of the form, you start out at state S0, and then what is the probability that you end up at state S n steps from now? So in order to answer these questions, we would need to compose probabilities at each time step. Classically, in a Markov chain, for example, this is done by a state transition matrix, which is a matrix consisting of probabilities associated to each pair of states. And this matrix is then multiplied, and its nth powers are used to calculate the transition probabilities from state S to state S to S prime for any two states S and S prime. However, formalizing matrices and matrix multiplication can become cumbersome. So it was natural for us to ask if there was an easier way to express the following operation. And the key idea which makes this possible is Kleisli composition in the Giry monad. The key idea being that the Kleisli composition of the Giry monad recovers the Chapman-Kolmogorov formula. Let me explain what that means. First of all, we introduce the type PMF, which I alluded to before, which is the type of discrete probability measures on a type. This is also a record of containing two fields, which is a list of outcomes, and along with the predicate that the probabilities consist of sum to 1. The outcomes pair up a finite list of elements of A along with their probabilities of occurrence, and the predicate sums up the probabilities and enforces that they sum up to 1. Now, on such a type, we define two basic operations. This is the return, which takes an element of the type big A, and then returns the probability measure, which concentrates all mass at the term A. And another operation called the bind, which takes a probability measure, a function which maps from a type to from A to the type of probability measures on B, and then marginalizes over the intermediate distribution in order to return a probability measure on B. So these two operations, the bind and the return, satisfy monad laws, making the triple P, bind, and ret into a monad called the Giry monad. This is also called the finitary Giry monad or the distribution monad. Now, given two such arrows, F from A to P of B and G from B to P of C, Kleisli composition, which is simply composition in the Kleisli category of the Giry monad, puts F and G together in order to return an arrow from A to P of C. And this is how it is defined. The fish operator, which this operation is called in Haskell parlance, simply binds F of X with G, where X is any starting state in A. Now, if you look at the summoned in equation 6, that takes F XB and multiplies that with GBC. This we can think of as the probability of starting at X, going to B, and then going to C. Now, if we sum over all possible intermediate states in B, we get the total probability of starting at X and then going to C. So this definition is exactly the Chapman-Kolmogorov formula. And so thus we've recovered the Chapman-Kolmogorov formula as Kleisli composition of the Giry monad. Now, how does this relate to a Markov decision process? Well, for a fixed decision rule, we get a Kleisli arrow, T pi, from states to probability measures on states, defined as the following. If you recall the type of T, it takes a state, it takes an action, and then it returns a probability measure on states. So in this case, we start off at a state S, and then we apply the decision rule, which takes that state and returns an action. And then we apply both of that to the transition structure T in order to return a probability measure on S. So this term type checks. Now, since we have such a Kleisli arrow, we can iterate this using Kleisli iteration, and K4 Kleisli iterates of T pi then give us at time T the entire transition structure after time T. Now, since this is a probability measure, we can integrate with respect to it, or in other words, we can find the expected rewards at the end of time k. And this is simply given by equation 8. We take the expectation of Rs by S, which is the reward of starting at state S and performing action pi of S, and summing this over all possible states and taking the expectation over it with respect to the probability measure after k steps, we get the expected reward at the kth step. Okay, so now we do this for all possible time steps from k equal to 0 to infinity, and then we gamma discount each of them. And then once we sum them, we get what we call the long-term value associated with the policy pi. This is expressed in equation 9. Now, the most important property of the long-term value v pi is that it satisfies the Bellman equation. The Bellman equation in words, which is given by equation 10, says that the long-term value is given by the immediate value plus the discounted future value, which is the second term. Now, this can be proven simply by expanding out equation 9 as an infinite series and then writing out the definitions. However, the most important property of this is that v pi occurs on the left-hand side and also on the right-hand side. And this is made more apparent by defining the operator b pi as in equation 12, which takes any operator from any functional from S to R to the immediate reward plus the the discounted future reward of W. And one sees that v pi is the fixed point of this operator b pi. Now, if we recall, the objective of a reinforcement learning algorithm was to find a policy which gives the best long-term value. And the key idea behind this is expressed by Bellman's principle of optimality, in which an optimal policy has the property that whatever the initial state and the initial decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. Now, expressing this in equations, we get the equation for V star, which is also a similar Bellman equation, in which V star appears twice on the left-hand side, on the right-hand side, and the maximum is taken over all possible actions available at the initial state of the reward available at the moment after the initial step, plus the gamma discounted expected value of the long-term value, the best of the optimal value function, V star. Again, V star is a fixed point of the operator B hat, which is defined by abstracting over the V star on the right-hand side of the equation which V star satisfies. Okay. Now, the most important property which makes all of the theory tick is that the operators which I defined before, B pi and B hat, are contractions with respect to the max norm on the function space S to R. And also, another property which we know is that the function space from S to R is a complete metric space with respect to the norm, with respect to the metric induced by the max norm. And we've seen that V pi and V star are their respective fixed points. Now, the Banach fixed point theorem says that function iterates of a contractive map converge to its fixed point. And so, since we've exhibited a fixed point of these two contractive operators, we have found a recipe to approximate them via the Banach fixed point theorem. And these V pi and V star are unique because fixed points of a contractive operator are unique by the Banach fixed point theorem. Now, another important property to note that we can immediately recover the optimal policy once we know the optimal value function V star. This is simply by by finding the action which gives the optimal value of each at each state. So as I said, this gives us a recipe to compute V star and hence also the optimal policy. So value iteration is an algorithm which proceeds by initializing a value function V0 and then defining iterates Vn plus 1 inductively as function iterates of the operator B hat. And in computing B hat of Vn, we also compute at each stage the greedy policy pi of n, which is given by the argmax of this term in the parentheses. So value iteration simply proceeds. So this slide gives you the pseudocode for value iteration. And the one thing I want to point out is that it depends on a threshold theta. Value iteration has a stopping condition, which is enforced by this threshold theta. At each stage, once the iterates Vn are computed, you also check if the iterates Vn, if the iterates Vn plus 1 differ from Vn by a threshold value theta, then we stop. So this is because the convergence of value iteration is an asymptotic convergence statement. And so this threshold is necessary. Policy iteration, on the other hand, is a similar iterative algorithm that benefits from a more definite stopping condition. So if we define a Q function, which takes a state and an action and returns the reward, the immediate reward at state S by performing action A, along with the gamma discounted expected value of the value function associated to policy pi. Then policy iteration simply proceeds by initializing a policy to pi 0, and then performing two steps called policy evaluation and then policy improvement. Policy evaluation simply evaluates the value function associated to a policy, and policy improvement computes a greedy policy pi n plus 1, starting off from policy pi n. Now, the algorithm continues until V pi n is the same as V pi n plus 1. And as soon as that condition is satisfied, the algorithm stops. Now, termination is a consequence of the fact that policies are finite. And because of the following, because of the fact that in step 3, the improved policy or the greedy policy is a strict improvement of the one constructed before. Or in other words, the value function of V pi n plus 1 is greater than or equal to the value function of V pi n for all states S. And this was the key property which makes policy iteration converge. And this is a property which we formalized in Coq. Okay. Now, another important proof technique which we used in our convergence proofs for value and policy iteration is metric coinduction or contraction coinduction. So as we've said before, the convergence proofs rely on the classical Banach fixed point theorem, which says that if X is a complete metric space and phi is a closed non-empty subset of X, then if F is a contraction and if F preserves the subset phi, then F has a unique fixed point inside the subset. And it also gives us an algorithm to compute what the fixed point is as the limit of the nth iterates starting off at any point x0 inside the complete subset phi. Now we can restate this as this proof rule, which I can read as saying that if phi is any closed non-empty subset of the complete metric space X, which is preserved by phi, then the fixed point of F also belongs to phi. Now, stated this way, this is the Banach fixed point theorem is called Dexter-Cosen's metric coinduction principle. It is coinduction because it is equivalent to stating that a particular coalgebra is finite in a category of coalgebras. However, it is important in our formalization because it helps us streamline and simplify proofs of theorems about streams and stochastic processes. And it allows us to automatically infer that a given closed property holds in the limit whenever it holds when we're starting out. Typically, most convergence proofs in which we want to prove a particular property of a fixed point proceed by low-level epsilon delta arguments. But the metric coinduction principle exploits the fact that the work has already been done in the proof of the fixed point theorem to infer that the property holds automatically off the limit when it holds initially. And so we can perform reasoning at a higher level of abstraction and the proofs become algebraic instead of analytic. We use in our proofs a specialized form of metric coinduction called contraction coinduction, following the paper of Fays, Hansen, and Moss, and our proofs also rely on some of the proofs they make in their paper. And contraction coinduction states the following. If X is a non-empty partially ordered complete metric space in which the sets of the form X such that X is less than or equal to Y and X such that X greater than or equal to Z are closed for all Y and Z. And if F is a monotone contraction operator, then if f of X is less than or equal to X, then the fixed point of F is also less than or equal to X and its dual statement, where X star is the fixed point of F. So order statements concerning fixed points can now be easily proven using this proof rule. And here is an example of where we use contraction coinduction. The left-hand side is an English proof of a result taken from Fays, Hansen, and Moss's paper. And we've the proof, the English proof shows that the greedy policy, which we've constructed before, is the policy whose long-term value is the fixed point of B hat. And the right-hand side is a Koch formalization of the same theorem. And one can see that the Koch formalization and the English proof are almost the same size and also at the same level of abstraction. So formalizations using contraction coinduction can be very pleasant. Another example where contraction coinduction helps us avoid unnecessary details is in the proof of the policy improvement theorem, where, if you recall, I stated that we need to prove that the policy improvement is actually, the improvement step is actually an improvement. What you see on this slide is a proof of the policy improvement theorem given in a textbook, a canonical textbook on reinforcement learning. It says in the second sentence that we start from 4.7 and we keep expanding the q pi side with 4.6 and reapplying 4.7 until we get v pi prime. Now, without looking too much into the details, this proof roughly says, exhibits that the property of that A is less than or equal to B holds of every partial sum. And because the matrix space is complete, all of the partial sums actually converge to the fixed point, which is v pi prime. But this reasoning is unnecessary because, as I said, the work has already been done in the proof of the Banach fixed point theorem. And so one can automatically conclude order statements of fixed point theorems using the proof rule of contraction coinduction. All that's remaining to show is that the operator f satisfies f of x is less than or equal to x, and then we will be done. Okay. So as concluding, we have proved convergence of classical value and policy iteration algorithms in COC. And for infinite horizon gamma discounted Markov decision processes. We have also in our formalization, we considered the finite time case, and we dropped the non-stationarity assumption, and we compute optimal value functions for a finite horizon MDP. And this is typically what is done in practice. Because convergence of value and policy iteration is asymptotic, we also looked at the finite horizon case, and we proved that that we can also compute optimal value functions in that case. Our formalization shows that using the Giry monad and contraction coinduction, one can simplify and streamline proofs. And as future work, we are currently looking at stochastic approximation algorithms for model-free reinforcement learning algorithms in which the transition structure of a Markov decision process is not given to us a priori. I thank you so much for your attention, and I'll be happy to take questions.